Witam po krótkiej przerwie. Żeby nie przedłużać, zapraszam na scenę kolejnego prelegenta, pana Krzysztofa Opasiaka. O czym opowie, to już powie sam.
So, hello, welcome everyone. My name is Krzysztof Opasiak. I work for Samsung R&D Institute Poland. In my daily job, usually I work with Tizen OS. I'm working on the USB support in it. And today I would like to tell you a few words about building your own USB device on a cheap Linux board like BeagleBone, like Odroid or Orange Pi, all the stuff like this. So the schedule. Sorry for the delay, but it's a problem with some proprietary OS, so we cannot debug it. First of all, I would like to give some gentle introduction to the USB protocol itself. Then we will try to compose a USB device from ready building blocks from the Linux kernel. And then we will try to create our own custom building block, which is called the USB function. Then there is going to be some short summary and the Q&A session if we have enough time. Okay, so generally what USB is about? In my opinion, USB is about the same thing as the internet. USB is about providing a service. Of course, different types of service. In internet, usually you have the web pages, you have the video streaming, and in USB, you have a little bit more low-level services. We have the storage, we have the printing, we have the Ethernet over the USB. All that kind of stuff can be used from the USB device. What is the architecture? Well, in comparison to the internet, we have two different sides of the communication. We have the USB host and the USB devices. USB device is a provider of the service. So we can extend USB host with some services offered by the USB device. USB device is often called a composed device because it may offer more than one service in the same time. So for example, single physical USB device can be in the same time the web camera and the pen drive. No delay. Okay, so what USB device itself really is? First of all, it is a piece of hardware for the USB communication. It's a little bit equivalent of the network card from the internet. If we are able to communicate with the host, then we need to speak a common language. So we need the implementation of the USB protocol itself. When we have this, we may create our own protocol on the top of the USB protocol. And of course, if we would like to provide some service, if we would like to provide some functionality, we need a piece of hardware or software, because we can emulate this, for providing this desired functionality. So for example, for pen drive, we need the flash memory to store the data on it. Okay, the communication in USB happens always between host and one of the endpoints. Endpoints are on the device side, so that's a little bit equivalent of the TCP port from the internet. So you connect to the TCP port, and here you send the data to some endpoint. Single device may have up to 31 endpoints. Of course, it may have less, but not less than one, which is called the endpoint 0. This is the only endpoint which is mandatory, because it is used to discover device capabilities when we connect the device. Each of the endpoints gets a unique endpoint address, so we can identify it. And endpoint 0 is the only one which can transfer the data in both directions. In TCP, when we have the connection to some specified port, we can both send the data and receive the data. In USB, we can do this only using endpoint 0, and all other endpoints are unidirectional. So it means that it may only receive or send the data. If we are talking about the direction of the connection, so in USB, we always mark the direction from the host perspective. So if host is able to send the data to some endpoint, we call that this is the out direction. If host is receiving the data from some endpoint, it is the in direction. Okay, in internet we had only two options. Usually we had the TCP and we had the UDP protocol. In USB we have 4 different types of transfer. First of them is the control one. It is reserved for endpoint 0. It is used to discover device capabilities, but also can be used later by the application. The next one is the interrupt transfer. It is used to transfer a small amount of time-sensitive data. So, for example, your keystrokes or your mouse movements, they are all transferred using the interrupt transfer. The next one is the bulk. It's the most common one because it is used to transfer a large amount of time-insensitive data. So it means, okay, here is a bunch of data, so please transfer it when the bus is free for me. The next one is the ISO. It is used to transfer a large amount of time-sensitive data, like the video stream. The only restriction here is that the delivery is not guaranteed. Okay, how does it look, the logical device layout? We have the USB device as a whole. We have the endpoint 0, which is the only one which is mandatory, and it is not grouped into interfaces. And all other endpoints are grouped into interfaces. Interface is defined as a group of endpoints which has to be used to provide some well-sandbox functionality. Interfaces are grouped into configuration. All the interfaces in single configuration can be used in the same time. Device may have multiple configurations, but only one of them can be active in the same time. If the configuration is active, we may use all its interfaces. USB bus itself. USB is a host-controlled bus. It means that nothing on the bus can happen without host first initiating it. Even if we are talking about the in transfer, so when the device is sending the data to the host, it is initiated by the USB host. How exactly it looks? Well, the transfer of the data is split up into transactions. Single transfer consists of multiple transactions. And the transaction is the delivery of data limited by the endpoint size. So it's usually, for example, 500 bytes, nothing more. Transfer itself may be really large, for example, few megabytes or few gigs. That's not the problem. And the transfer is a set of consecutive transactions, and it ends up when the desired amount of data has been transferred. So host declares, okay, I would like to transfer 5 megabytes and nothing more. When the transfer is ready, it is the end of the transfer. The transfer may end when we have a short transaction. Short transaction means that it is the transaction which is smaller than the endpoint size. Okay, how the in transaction looks like. If host would like to receive the data from the device, it sends the in token to the device. If device has data, it simply replies with the data. If it doesn't, it sends a NAC. It's a short token which is defined by the USB protocol. If host receives the NAC, it goes up here and sends the in token once again. So USB is a polled bus. We are polling the device for the data. Do you have the data? Do you have the data? Do you have the data? Okay, now you have, okay, thank you. If you would like to send the data to the device, host sends the out token, then it sends the data, and if the device was ready to receive the data, it sends ask. If it was not ready, it sends NAC, and host is doing once again the same thing. So it's really painful for the bandwidth That's why we have in USB 2.0 we have the bandwidth savers, the ping and not yet commands, so we can skip this sending this data all the time because this is a single byte. So that's not a problem for the bandwidth, and this could be large. Maybe not so large, but 500 times bigger than this. So it's painful. Okay, the most recognized feature of the USB is the plug-and-play philosophy. So you have your USB device, you may connect it to your computer, and everything happens automatically. How it is done step by step. First of all, we need the user action. We need to plug in the device, and host need to detect the connection. This is done usually by the hub, and even itself it's served by the driver. We need to set address because each device on the USB bus has its own unique address, which has been chosen by the host. So this is a single byte, and with the bit mask, so we may have up to 127 devices on a bus. We need to learn something about the device, because when we connect some machine, we don't know what is it. So we have to ask it, okay, you are a pen drive, or you are a camera, or whatever you are. When we have this information, we may choose one of the available configurations and choose a driver for interfaces. Yes, this may be weird, but in Linux, we have the driver for each interface separately, not for USB device as a whole. Why? Because USB device may be a composed device. So it may offer multiple functionalities which need multiple drivers. The example from the beginning, we have the device which is in the same time a USB camera and the USB pen drive. So that's our two different drivers. Okay, how does the device details look like? First of all, each USB entity word is described by the data structure called the USB descriptor. It's a family of data structures, and they all share the common headers, so it's a kind of polymorphism. And that's why we can easily iterate over all of them. We have the USB device. And this device as itself is described using the USB device protocol, USB device descriptor. And the first field of it is, maybe not the first, but one of the most important fields is the ID vendor. ID vendor is the manufacturer identification assigned by the USB organization. So it allows us to mark, okay, this device is mine. We have the ID product, so it's the identification of the product, but not the product, the model as you buy in the shop. It's the identification of the USB product. So the version of the USB protocol, it's here encoded together with the BCD device and that stuff. If our device implements some well-known protocol, well-defined, there is a standard, so we comply to, and we don't need a special driver, we would like to use a generic driver like all the pen drive does, so we may use the device class and subclass. The same information is in interfaces, because we may, each interface may belong to different class, so we need a different driver. And we have the human readable strings for learning who is the manufacturer, the product, and what is the serial number. Of course, it is not mandatory to provide different serial numbers for each device. So we may have 100 devices with the same serial number. Configuration descriptor, the Bmax power is an important field here, because in each configuration, our device may drain different amounts of power from the host. Why? Because in one configuration, we may not charge our smartphone, and in other configuration, we would like to charge our smartphone as fast as possible. In each interface, we have some number of endpoints, the string, the subclass information, and the endpoint descriptor. We have address and the information, what is the type of the endpoint. So is it control, is it ISO, is it bulk, or anything like this. And of course, the size of the endpoint. What classes are available? We have the audio, communication, all those standard devices which you know from your daily routine. are defined as classes, so you don't need a special driver for each pen drive, you just use one generic mass storage driver. But what this driver really is? Well, first of all, when I'm talking here about the driver, I mean a driver in meaning of piece of kernel code. Of course, it is possible to write a user space equivalent of the driver using libusb, but here we focus on the kernel drivers because they are most common. Usually, such driver is only a translation layer between USB device and its protocol, like mass storage, and our Linux protocol, which is called, for example, block device. So we provide this driver provides something to user space, and user space uses this entity like the network interface, like the block device, and this driver simply translates the request from the user space into USB protocol and sends it to the device. Such driver is described using the struct USB driver. There are different structures which has the USB and the driver word in its name, but this one is important for us. And how to choose this driver? We have many drivers, we have to choose one. Well, first of all, if our device needs special handling, usually we will use the vendor ID and the product ID. That's why people and the companies are paying for the vendor ID, because they are able to know that to provide a custom driver for some particular device. That's why we are paying for it. If our driver implements some well-defined standardized protocol, then we use the class information from the interface or from the device. Thanks to this, some Chinese or some other cheap producers do not buy the vendor ID or the product ID stuff from the USB organization. They place some invalid data, but they place the correct data about the interface class, and the pen drive is working because the driver is chosen using the interface class information. How it looks in the big picture? We have our phone, for example, connected to our computer. We have the host controller, the piece of hardware on the host side. We have the driver. We have the struct USB device. We have the USB interfaces and a driver for each interface. These drivers provide something to user space, for example, input source for our X11 if it is a keyboard, or the network interface. And we can use this using our web browser. Probably we'll get configured using our network manager. Okay, so how we can build our own device, our own USB device? What do we need? Well, first of all, we need a suitable hardware. We need to be able to communicate with the USB host on the electrical level. So, of course, we might build our own one, but the easier way is to buy some Linux board with the USB device controller. Such boards are, for example, BeagleBone Black, Odroid, Orange Pi, all the stuff which is marked that it has the USB client port. Raspberry Pi is not working, sorry. We need the implementation of the USB protocol. We may use the one from the Linux kernel, because why reinvent the wheel? Then we need the implementation of some useful protocol. If you would like to provide some functionality to the host, we need to communicate somehow. So this is the communication protocol, and we need to know this. We need to have its implementation on the both sides. On the host side, it is called the USB driver, and here we are focusing on the device side, so we need to implement the other side. Then, of course, we need the desired functionality provider. This is our executive element, so like the flash memory in the pen drive. We need a place to store the data somewhere. Okay, some short terminology. The USB device itself can be split up into two parts. First of them is the USB device controller. It is hardware dependent, the piece of hardware for communicating with the USB host. Then we have the hardware-independent layer, which is the USB gadget. It is USB-level implementation of the USB device. It's hardware-independent. The same code is working on multiple devices. USB gadget consists of USB functions. USB function is a driver which implements some useful protocol. For example, it implements the heat protocol. For example, it may implement the mass storage protocol, or many others. And the USB gadget itself is only a glue layer which allows us to put multiple functions into a single USB device. How it looks in the big picture. We have the USB bus and our host, the UDC driver, and of course the hardware. Earlier, we have the USB core with some helper functions. Our USB gadget which simply routes the communication to suitable USB function. And the USB function should look similar here to the USB driver because it also provides something to the user space, so our device side user space, like on your Android phone when you are doing the tethering, on your phone the network interface will appear. Okay, prerequisites. What do we need in our kernel to use this feature which I will be talking about? You go to the device drivers, USB support, USB gadget support. You should choose the USB gadget drivers, the USB functions configurable through config.fs, and mark the functions which you would like to use. What kind of functions are available? First of all, we have the Ethernet emulation, so the Ethernet over USB, serial functions, mass storage, so the pendrive equivalent, human interface, video class, so we may introduce ourselves as the camera. We have the audio class, printer, some old Nokia protocol called Phonet, and some developers protocol, loopback, and the sourcing. What does it mean to compose a device from those functions? Well, first of all, we need to choose the identity for our gadget. We need to fill the values from the USB device descriptor. We have to decide which function we would like to share with our host. We need to decide how many configurations and which function should be available in which configuration. How to do this? We have many different options. First of them is to use the bare kernel interface, but it's really tedious. There is a lot of file system operations. They are simple, but there is a lot of them. So there is a helper library. We can write simple C application and compose our device from the C code, but it's still the code. We need to compile it. Why to do this? There is a command line tool called gadget tool. We may use it to write a script, create gadget, create function, do anything, but it's still writing a shell script. And the last option, the best one, is to use a gadget schemes. What it is? Well, it's a simple configuration file in which you can declare, okay, please, this is what I would like to get, and do this for me. We declare the values from the interface, the strings, which functions should be available, and how many configurations. Okay, so how it looks in the command line. On the left side, I have the command line from my device, which is connected. This is the Odroid. I'm logged in here using the serial console. On the right side, it's my host computer. I'm currently connected using the USB, so immediately after configuring, I should see that my device is connected. I might show you here LS USB. This is what is now connected to my computer. And here we say just the file name. GT load G1. Okay, the logs here comes from the Linux kernel, and it means that the gadget has been created and we are connected to the host, and the host chooses the first configuration. Now on the host side, if we do ls USB once again, we will see a new device. It is over here. Because I'm using the Ethernet function on the both sides, I will get the USB 0 interface. It's of course unconfigured. Okay, it's painful to read, so maybe I will just set it up. Now I have put up the network interface on the device side, and I will do the same on the host side. Okay, what I have achieved using this? Well, for example, now I may log to my Odroid board using the SSH from the host. Okay. True. Now it should be working. Okay, so I have now logged using the SSH and the Ethernet over the USB. So we had already building blocks from the Linux kernel. We just take it, compose it into one device, and we are ready to go. We may use this, we may do this using a single configuration file, so it's quite easy. Okay, but what if you would like to use our custom protocol? For example, if we are doing some students project and we would like to connect some sensor to our PC or something, and we don't have a suitable protocol which is defined in some standard. Well, we need to create our own functions. We can do this in two ways. The first of them is to write a kernel function, just like those which we use to emulate the Ethernet. And the second option is to use a function fs. What's the difference? Well, here we write the kernel code, and here we are writing a simple user space service. When we would like to choose this, usually if we need the access to the system infrastructure, for example, to the file system, to the network interface, to dbus, or all other stuff which are hardly available from the kernel. What function fs is? Well, for the USB subsystem, it's a standard function, just like the internet. For us, as a users, it's a file system which forwards all the traffic related to this function to the user space via the file system. How to use it? The general concepts. Well, when we mount a new instance of function fs, we will get a single file. This file is called endpoint 0. It is used to communicate with the USB host using the endpoint 0 traffic. And from this file, we may also read the events. What are the events? Well, when we connect to the computer and host choose a configuration in which our function is available, then we will get an event enable. So this is the moment when we should start our communication with the host. If we read on some endpoint, we are scheduling the USB out transfer. So we say, okay, now I'm ready to receive the data. When the host would like to send me some data, I agree to accept it. If we do write, we schedule an in request. Of course, device cannot initiate any communication. So, for example, when we do write, we are not sending any data to the host. We are just telling the kernel, okay, when host will ask for the data, this is the data you should send to it. how to use functionFS. First of all, we need to create a function instance. This can be achieved as creating the standard USB device using GT or using all the previous ways. We need to mount the file system and pass the instance name of this function as a device name to the mount. We need to open endpoint 0, write function descriptors, write strings, open other endpoints which we would like to use for communication, read events from the endpoint 0, and when we will get the enable event, we should start our communication with the host. Then start the communication means read and write using the other endpoint files. Okay, so I have a short demo. What I have here is a simple chat protocol. It means that we will get the console on the one side and console on the host side and console on the device side, and we will be able to send some text messages to each other. Okay, so I will now reboot. What I have to do here is to log in to my Odroid also using the SSH, because I will need the other console. Okay, this is another console to my Odroid. So you see this using the prompt color. Here we have our standard one. Okay, device. It's a synchronous chat. The device one.gs, it's a configuration file, which you have seen on the previous slides. So I will load this using the GT. And I pass the -O option, which means, okay, just create this on the file system, but do not bind this to the hardware. So there is no connection between the kernel entities and the hardware, because we need to start our user space service before we will be fully prepared for the communication with the host. Okay, I have created the gadget. Now I should mount the file system. Okay, the file system has been mounted. So on the device side, I will start the user space service. I run it in the blocking mode. So this is the input of the program. And now I should be able here to enable my gadget. Okay, the gadget has been enabled. And on the host side, I will now run the libUSB application, which will allow me to communicate with my device, to chat with it. Okay. Now if I write something on the device, I will be able to read it on the host and the link-wise. And on the device side, and something went wrong. Happens. Okay. Doesn't matter. The source code of those examples is available on my GitHub. So if you would like to start with dealing with functionFS or with building your own USB device, check out the code on the GitHub. You can easily adjust it to your own needs. Okay. When I use the functionFS, in example here, on the device side, I used a simple way of writing a functionFS service. Simple means using blocking read and write. What are the consequences? The first of them is that when I'm waiting for the message from the host, I cannot send anything. To do this, I should use threads or I should use the asynchronous I/O. The easier way is to use the asynchronous I/O. So instead of doing the read and write and block until they are ready, I use the event file descriptor and I'm simply scheduling, okay, here is the read, here is the write, and I'm only waiting for the completion. Okay, some short summary and some, let's say, advice for those who would like to start playing with the USB. First of all, USB is about providing a service. If you have your microcontroller or you have something which you would like to provide to your PC, it's really a good way to use USB for it. The communication protocol have to be implemented on the both sides of the communication. We need a driver on the host side, and on the device side, we need the USB function. There is a lot of ready USB functions in Linux kernel, so usually if you like to do some basic stuff with the USB, everything should be ready and on its place, so you only have to configure this and start. That's all the thing. Instead of using the bare config.fs interface, I encourage you to use the helper library and the gadget tool because it is much easier. At least for me, it is much easier to write a simple configuration file and use one command to load it instead of doing about 10 or 15 make dir commands or symbolic links. If you'd like to implement your own function, consider using functionFS. Usually it's the good way to go. You should use kernel function only if performance is really, really important, or if you would like to use some kernel infrastructure, some direct access to the hardware, some interrupt handling, all that stuff. If you are using functionFS, usually you will have to use asynchronous I/O because it will be more flexible. And the last one, have fun with the USB. It's really a lot of fun, usually when it is not working. So USB may be called the universal serial bus, or the usually slightly broken. Unfortunately, more often the second one. So there is a lot of fun. Okay, do we have some time for the questions? I think yes. Okay, so if there are some questions, I will be happy to answer. Yep. Do we have the microphone? In the corner of the room.
Thank you for this very rich and enlightenment and full of technical details presentation. I really liked it. I have a question for you. What do you think are the current ways and maybe future ways of authentication of USB devices? How can we authenticate a USB device? Because we have number, nothing.
Okay, I know what is the question. Yeah. Well, the question is related to...
What do you think is the best way to do it?
The question is quite related to one of my talks from the Embedded Linux conference. You may watch this on the YouTube. In my opinion, the only reliable way of identifying the USB device is to use the USB topology. Because if you are plugging in, for example, your keyboard, usually you use the same USB port in the same USB hub. So if you mark that this is my serial number, this is my ID vendor, and this keyboard should be placed in that port, in that hub, usually you will not disconnect this to connect some pen drive. Because I think you are talking about the bad USB attack. which is the most common one in the terms of the USB. And usually this attack is based. Do you all know what is the bad USB attack? Or not? Who don't know? Okay, so the basics of the bad USB attack. You have a pen drive, and this device looks like a pen drive, smells like a pen drive, feels like a pen drive, but for your USB host is a USB keyboard. No, it's not a pen drive. For it sends the descriptors quite similar to your keyboard from your desk. It may send, to be honest, the same descriptors, not only similar. So for your host, it's the USB keyboard, not the pen drive. So there is no relation between physical outfit and the implemented functionality in the USB. All the drivers are chosen based on the values from the USB descriptors, and there is no any digital signatures, there is no cryptography, so device may send anything what it wants. And this is the bad USB attack. Currently, there are some methods of blocking this attack. None of them is perfect, but the most common approach is to use programs like the USB guard. You may check it on the GitHub. What is it? Well, it uses the device authorization, because usually in the common scenario, when we connect the device, everything happens automatically. And USB guard uses the USB authorization feature from the Linux kernel. It means that probing of the drivers for the device is delayed until user will check that this is really the device he would like to use. So that's the answer. And the way of checking if this is the device I would like to use, well, it depends on you. It depends how much security you would like to join, if you would like to only control if this is a pen drive or if this is a keyboard. So you may use simply LSUSB and say, what is it? If you'd like to be sure that your keyboard is really your keyboard, not the keyboard hacked by someone else, well, if you allow anyone to disassemble your keyboard, then okay, you have a real problem.
Okay, as we have not much time, one more question. No questions? Okay.
Okay,
So
thank
you
you
very much. Wait a moment, because